In the last few videos, we've been looking at linear Gaussian state space models, and in particular, how to perform filtering in them using the Kalman filtering recursions. In this lecture, we're going to switch gears and we're going to look at discrete hidden state HMMs instead, rather than continuous valued HMMs with continuous valued latent variables. And we're going to derive the algorithm to do filtering in this new context. And that is called the forward algorithm. And you see, again, because these algorithms were developed in different communities, they have very different names, but fundamentally, the steps involved in each are extremely similar. And you can see that here by this sort of bird's eye view of the algorithm. It has the same steps as we have inside the Kalman filtering recursions. It has a prediction step, which is shown here, and it has an update step here where you take your prediction for the next variable and multiply it by the information coming from the current observed variable, the likelihood, and renormalize. Okay, and we're just going to walk through these steps now for the case where the hidden state is discrete. So in particular, if you remember, it's going to take one of k values. So each x can take values in k equals 1 through to big K here. So the distributions that we'll be dealing with at each step will be categorical distributions that simply are a vector which tells you what's the probability of being in each one of the states at each time point. And we're going to use a similar notation that we used for the Kalman filter here, whereby rho is going to indicate the probabilities in these categorical distributions. The subscript of rho will indicate which random variable the distribution is over. So here it's over xt minus 1. So the subscript is t minus 1. And the superscript will indicate what observations we have used to compute that filtering estimate. So here we use superscript t minus 1 because we've used all of the data up to and including the t minus 1th time step. Okay, great. So these are the distributions that we're going to propagate and update via the forward algorithm. And the goal is to apply the two steps we talked about to compute this quantity, which is the updated rho, which we could denote like this. So it's the filtering distribution over the tth latent variable xt, given all of the information up to the tth time step. Okay, so hopefully the setup is clear. Let's talk about the two individual steps. And the forward algorithm is actually much simpler in terms of the calculations that are involved than the Kalman filtering updates, because we just are updating vectors of probabilities and manipulating them using tables of probabilities. Okay, so the first thing we have to do is make this prediction for the latent variable at time step t, given all of the data up to and including yt minus 1. And we know how to do this. We've actually looked at this. This is things we've encountered in Markov models a lot of the time. We know that in order to evolve the distribution here, we just take the distribution at the previous time step here. So this is the filtering distribution that we have above. And we pass it through our conditional distribution of ending up in state K, given that we're in state L. So this thing is our transition matrix, TKL, and is part of the model. And this thing here, of course, on the right-hand side, is just our distribution rho. Great. Okay, so we can substitute these things into these expressions now, and that gives us our first step in our forward filtering algorithm. You just take the vector of probabilities from your filtering distribution and hit them with the transition matrix. Do that matrix multiply, and that gives you your forecast for the next step. And in general, you could forecast tau time steps into the future using exactly the same expression by hitting that matrix rather than once with the transition matrix hitting it tau times. So this is sort of the general recipe for how to do forecasting in these models. Really, really easy. Great. And now what we need to do is combine this with the likelihood function. So again, let's just walk through that in a bit more detail. The prior is just given by forecast estimate. So we substitute that in here. It's our prior distribution, how likely we are to be in each one of the case states. And then we reweight it by our likelihood. And this can take different forms. So if you've got continuous valued y's, this would be multiplying by some distribution, like a Gaussian distribution, for instance, whose values depend on the observed data. Remember, the data are fixed here, so we're given the y's, and we just evaluate that distribution for different settings of x. If we have discrete values for our y's as well, then this ends up being multiplied by just those discrete probabilities that are in a table. So again, reasonably easy to calculate this. This is very similar to the inference we were doing in a mixture of Gaussians model, where this is playing the role of the prior, how likely you are to come from each one of your Gaussians, and then this is the likelihood contributed from each Gaussian component. It's exactly the same structure that we met in the mixture of Gaussians clustering, but now in this temporal setting. That is if the observation model is a Gaussian. Good. Okay. In general, you have to be a bit careful when you implement this. So if we look at this, we just need to implement this line and this line on a computer. So just two lines, simple to implement the forward algorithm with those that live inside a loop with some sort of initialization to get things started. In practice, you have to take care when you implement these things. It's easy to run into numerical underflow or overflow. You're constantly multiplying here by densities, which could be really, really small or could be really, really big. And that can cause numerical instabilities. So there are good, robust implementations out there and a bunch of tricks. One of them is famously called the log sum exp trick, which are used to numerically stably compute these quantities. So if you're going to go and sort of play around with these things and implement it, make sure you do it in a numerically stable way. And there are lots of guides about how to do this. But from a high level perspective, it is a fairly simple procedure that involves a bunch of matrix multiplies essentially.